evaluate the two functions, set it to be 1, solve for the constant, and then that yields our shape function. The two surfaces individually would have been planes had we just thought about our y minus x and our y equations. When you multiply those together, you get a quadratic function. So this particular shape function only needs to be quadratic. Problem 2 is a plane stress square element. Here I've laid it out as a double unit square, so it has these nice coordinates for the nodes. The question is to find the shape functions for this square. When we discuss the solution, we should recognize that there are 2 degrees of freedom per node in nodal coordinates. There are 2 field variables, u and v, that we're trying to interpolate. The shape functions n will be used for both the u and the v interpolation. Now, for a given shape function, it will require a unit value at one node and 0 values at 3 other nodes. That's a total of 4 conditions. So the polynomial will have to have at least 4 generalized coordinates if written out in the form a plus bx plus cy plus dxy, let's say. Now, that's only an observation. We're actually going to use a product form which may have slightly different form, but you can see that there's a need for a certain amount of adjustability in the coefficients here, namely enough to give 4 conditions. The next figure is rather busy because I work out all 4 shape functions on it. Over here is a sketch of the element. And basically what we're going to do is use the product form where we can see that a shape function such as n1 should have a unit value over its home node, and then we can run these lines that pass through the other nodes. So I'll draw a red line through this pair of nodes here, and there would be an equation for that line, namely 1 minus y equals 0 here. Then another line here, which is just 1 minus x equals 0. And then we can build in all 3 of those zeros in this product form. By allowing an adjustable coefficient c, we can make that fix the amplitude over the home node to be unity by setting 1 as c times this function evaluated at the home node, and we'll get the coefficient to be 1/4. That leads then to this shape function here. The dimensionality has been suppressed a little bit because we have used, rather than reference numbers such as a and b, we've used unit values. So the dimensionality here is perhaps a puzzle, but is okay in this particular case. X and y run from 0 to 1. You might think of them as non-dimensional ratios themselves. Then we follow that same reasoning for the second, the third, and the fourth shape functions and get all 4 of them. This approach is actually called the serendipity approach to finding shape functions, and it means that you kind of luck out. It was based on the princes of Serendip, which is really Sri Lanka nowadays, that apparently went off on their horses in wild adventures and always came out smelling like a rose, even though they managed to goof off a little. The process that we've done here is really important for a topic later on called isoperimetric elements. So I'm giving it to you a little bit unmotivated here, but you can see that it's relatively easy to find shape functions on a double unit square. The third problem is to find shape functions for a constant strain plane stress triangle. Here I've embedded the triangle into the xy space away from the origin and given it these coordinate values at the nodes. The idea is to find the shape functions. So the solution involves, again, finding equations for the lines that bound the element, because we'll use those to force the shape functions to have the proper zeros. In the next figure, I'll work out the three shape functions for this triangle. Again, we'll use the product rule that depends so heavily on finding the lines that define the zeros that are needed. So the three equations for the straight lines passing through the element sides are given here. Of course, the easiest one is y equals 1 at the bottom. But let's start out looking at the shape function n1 of x and y with home node here. Then it should pass through 0 on the opposing two nodes. The way to do that is to build in the surface that passes through this entire line with 0, and that line y equals 4 minus x can be built in then as a function here with our arbitrary constant. Then we evaluate the constant by looking at the home node, setting the constant to be whatever makes it true, and that's 1/2. We get the 1/2 value here, and we get our first shape function. We continue this for the other two, where shape function number 2 has to have 0 along this line here, and then finally shape function 3 has to have zeros along this line here. And we've ended up with linear shape functions, which would be expected in a constant strain triangle like this. Well, that ends our lecture for today.